This is Sangeeta Gulati, and we are here to explore trigonometric functions with GeoGebra. Let's see how we can plot the graph of trigonometric functions as a point moves around a unit circle using GeoGebra. So here I have the GeoGebra file open with the algebra perspective, and we are going to start by plotting a unit circle. So for that, let's take the circle tool. Circle with center and radius. Center is going to be the origin. So I'm going to click at the origin and pick the radius to be 1 unit. There we have our circle. Let's take a point on the circle which is going to be a moving point. So as you can see, it's now plotted in blue, and if I drag it around, it's free to move around the circle. We need one more point, and that's going to be the point where this circle intersects the x-axis. So if I take the point of intersection and if I select circle and I select the x-axis, then I'm going to get 2 points of intersection, C and D. I need only one. So I'm going to just hide the point C. So let's unselect that. And now I have point A, D and B. We are going to make an arc between D and B along the unit circle. So circular arc is the tool available. Select the center and the 2 points in that order. So we get an arc DB. It's not very clear as to where is the arc and where is the circle because they both are coming in black. So I'm going to change the color of the arc, going to the graphic properties. Let's make it red and just make it a little more bold so that it's easy to see. There. Now we are almost ready to start with the actual plot. So what are we going to do? We are going to look at two measures. One, which is the arc length. So what's the arc length of the arc DB? Well, GeoGebra calculates it as soon as you plotted it. Here it goes. So in the algebra view, you can see the arc D is equal to 0.9, and that's the arc angle, right? It's a unit circle and we have an arc angle. So if I take the coordinates of the point B, which in this case are going to change as the point B moves around. If I plot the arc angle against the coordinates of the point B, something is going to happen. Let's try it out. So here in the input bar, I'm going to plot D, comma, so D is the abscissa, and I'm going to choose the y coordinate of the point B as the ordinate of this new point. If I press enter, I get the point E. And in the algebra view, you can see that point E, x coordinate, the abscissa, is the same as the arc angle, and the y coordinate, that is the ordinate of the point E, is same as the y coordinate of the point B, right? So if I move this point B, well, E is going to change its position, it's changing its coordinates, and it's tracing a certain path. Can you guess what kind of a path it is? Yes, it looks like a wave, right? And as soon as I complete this one full revolution and come back to D, it starts all over again. So that's exactly what we were hoping to get. So if I take the point E and just for the clarity, let's change its color to green, and also on right click, I select trace all. Guess what's going to happen now? If I move the point D along the circle, the point B which is moving around the unit circle, the point E is going to leave behind a trace, and that is, my dear, nothing but the graph of the trigonometric function sine. So why is that so? Take a good look at the coordinates of the point E. It's nothing but, by the definition, the sine function, isn't it? Y coordinate of B is being plotted against the arc angle, and that's what we are looking forward to. Just to get you more understanding of it, I'm going to change the scale on the x-axis. And here on the x-axis, let's choose the labeling to be distance, but not 1 unit, but pi by 2. So now the markings are in radians. It becomes more easy for you to accept and understand this function. So this is how the graph looks like. And now you can observe that as soon as one full revolution is complete, the graph starts all over again. And that is what we call as the periodicity of the function. What else can you observe? Sure, when the arc angle is 0, the y coordinate is also 0. So we are looking at curve passing through origin. When angle is pi by 2, you are looking at the value of the graph taking the height 1. So the maximum value is 1, the minimum value is -1. Graph cuts the x-axis at pi, 2 pi, and if we keep repeating this cycle, then you will have more points where the graph is going to cut the x-axis. And that is the same thing that's going to happen on the other side. Now in this construction, since we are restricting the point moving around the unit circle, you're not getting the full wave. So if you repeat this pattern across the x-axis, you would get the full wave. GeoGebra lets you plot the sine function directly as well. So in the input bar, I'm going to type in sine of x. And if I just type in sine of x here, that's your wave that you will be getting used to and be exploring more and more. So I'm going to just zoom it a little out so that it becomes easier for you to observe. And here on both the sides, you can see the graph running like a wave wrapped around the x-axis. Let's hide this for the time being and now get back to plotting the second function, cosine function. So what should be the coordinates of the point now? D, of course, the arc angle, and against it, I'm going to plot the x coordinates of the moving point B. There, I have another point F. Let's observe its behavior as I move the point B around the unit circle. So keep an eye on F, right? Now, again, it's behaving like a wave, right? And after one full revolution, it again starts. So let's try to trace this path and see it a little more clearly. So right click on the point F, and if you want to change its color, let's do that as well. Here. Now if you move the point B around the unit circle, you get your second wave there. Isn't that beautiful? Let's also see how easy and how beautiful it is to explore the trigonometric function of tangent. So D, and I'm now going to plot y coordinate of B divided by x coordinate of B. Isn't that going to give us tan function? So if I do that, I get another point. Let's erase the previous traces. Keep an eye on this new point, which is G, and let's select the trace, and let's change its color. Which color do you want? Okay, let's me take something as maybe light blue, and let's move the point B around the unit circle. There. So you have the third function coming up as well. Now the tan function is very different from our wave like sine and cosine. What can you discover? Does it have a maximum and minimum value? And it's not continuous, right? It's breaking at some points. So remember what the domain of the tan function is. You're looking at all these multiples of odd multiples of pi by 2, not part of the domain. So there's a line of discontinuity at pi by 2, 3 pi by 2. And if I take the full function plotted directly rather than moving around a unit circle, so I'm taking tan x, and this is what you would have, right? So it's a pieces, but they're all being replicated at an interval of pi. So tan function has the periodicity of pi, cosine and sine have periodicity of 2 pi. There is a lot more that you can discover as you use GeoGebra. Try and do that. Let's see how you can plot the graph of sec functions, cosec, cot. Just a little tweak and there's so much more that you can do. I'm going to leave that for you to explore, and I hope you've enjoyed watching this. Go give it a try.